So, today's topic of discussion is the precise definition of a limit and using it to solve questions like these. Before I begin solving this example that I've written, I'll be going over one simple example and one sort of more complicated example. And before I do all of that, I'm going to give you some more sort of mechanical steps to approaching these problems. So, for this first problem, this is the sort of mechanical step that you can follow. The first part is let epsilon be greater than 0. This is sort of, if you state this down, you're almost guaranteed a mark because this is something that most students miss out on. So following the definition of the limit, you always have to let epsilon be a number greater than 0. The next part is let f of x minus L be smaller than epsilon. In this question, we're always given f of x, which is 3x plus 5 for this example. We always know L, which is 35. And we have to let it be smaller than this epsilon that we've taken from step 1. And this will all be more clear as I progress through solving that example. The next step is bringing this expression, the f of x minus L, manipulating it in some sort of way to bring it to look like x minus a. And this, again, will make more sense as I go through the process. And our final step is, once we have x minus a smaller than some expression, we should let delta equal this expression with epsilon. Okay, once we have that, now I will quickly solve this problem. Okay, so like I said, the first step is let epsilon be greater than 0. Okay, the next step is let f of x minus L be smaller than epsilon, like I just said 2 minutes ago. So we know that f of x is 3x plus 5. And we're also given the limit in this question, which is 35, which is always given in these types of questions. So we just write this out, which is 3x plus 5, which is f of x, minus 35, which is the limit, is smaller than epsilon. Just sort of simplification here, we put 3x minus 30 is smaller than epsilon. Simple. What we need to do now is use a series of processes, algebraic manipulation, so adding, subtracting, dividing, multiplying, anything to bring this expression 3x minus 30 to look like x minus 10 smaller than something, some expression with epsilon in it. And this one's a bit more obvious. So to bring it to x minus 10, what we can do is we can first factor out a 3 on this side. So if we do that, we get 3x minus 10 is smaller than epsilon. This will be different for every question, and you can factor out a 10 in this question, but you might not be able to factor out a 10 in another question. It's just something that's different for every question that you encounter. So you have 3x minus 10. You can, using absolute value properties, you can bring this 3 out. So you get 3x minus 10 is smaller than epsilon. Makes sense? Now we need to isolate x minus 10 on its own. So we divide both sides by absolute value of 3, which is just 3. So you get x minus 10 smaller than epsilon over 3. So, which is exactly what we wanted. We went from f of x minus L to some expression with x minus 10 to smaller than epsilon over 3. The last step in proving this limit is actually 35, is let delta equal whatever this expression is. Here we have epsilon over 3. So what we've done is we've proven that for any given epsilon greater than 0, there is a corresponding delta for which proves this limit. And I'll give a sort of proof for that, which will further clarify this. So once you've done this part of the question, I'm not sure if giving the proof for it is necessary. This is something you'd better ask your professor. So we're approaching x, where x is approaching 10, so x minus 10 smaller than delta, which is basically an inequality we had. From 2 minutes ago, or 2 seconds ago, I let delta equal epsilon over 3. Now, if we just do simple substitution, x minus 10 smaller than epsilon over 3. Okay, using cross multiplication, we get 3x minus 10 smaller than epsilon. Makes sense? Moving the 3 inside the absolute value, we get 3x minus 10, all absolute value, smaller than epsilon. And distributing this out, we get 3x minus 30 smaller than epsilon, and I'm sure you can see where I'm going with this. And the negative 30 is the same as positive 5. Excuse me. It's the same as positive 5 minus 35. So we get 3x plus 5 minus 35 smaller than epsilon. And from here, we know that this is f of x, and the limit is 35, which is L, which means that f of x minus L smaller than epsilon. Now, if you really focus on what I did here, the first part of my question was using the inequality f of x minus L smaller than epsilon to find a delta for every epsilon, which is exactly what I did. I went through a series of manipulations and I found that epsilon is any number greater than 0. If you pick any number greater than 0, for any epsilon, you can find a delta for it. So let's say this is 7. Let's say epsilon is, let's say 7, delta is 7 over 3. If you have epsilon is 0.1, delta is 0.1 over 3. Corresponding sort of pairs. The second part that I've done here, the sort of proof shows that you can start off with just x minus 10 smaller than epsilon, which is x approaching the value of a that we want, and using this that we found from the first part of the question, that delta equals epsilon over 3, you can use this to show that f of x minus L is smaller than epsilon, which is exactly what the precise definition of a limit says. Which says that we have to start from one point and get to the other. And we found a value for our delta, which lets us do that. So this was a sort of a more simpler example and how to approach it. I first showed using f of x minus L smaller than epsilon that we can find a delta for every epsilon. And the second part of the question, I actually proved that by starting off with the delta, subbing in my epsilon value, and then showing that the f of x minus L is in fact smaller than epsilon. In the next part of this video, I'll go over the same thing, but a more sort of complicated example.